We might be on this one for a while. Don't worry. We'll be fine. So the curves R of t equals stuff and S of t equals other stuff intersect at time t equals 0. There's parts A and part B. So the picture here is we have two curves in three-dimensional space, and we can sort of do a quick sketch. At least we can try to sort of build up our intuition. But one curve is R of t, and it's doing whatever it does. Here's R of t traveling along. And there's another curve, S of t, doing whatever it does. Here's S of t. And then it's like, aha, it just so happens that at one particular time, these two are in the exact same location. If we were thinking about these as particles traveling through space, we've just had a collision of particles. All right, so part A. Find cosine theta, where theta is the angle of intersection of the curves at time t equals 0. All right. Well, there's a couple of things we have to think about. But first off, does anybody have the answer? Did anybody work this out? There's a hand back there. Yes?
Not sure if it's right, but 17 over 9 times square root of 5.
17 over 9 times square root of 5. It could be an answer. I mean, it's at least between -1 and 1. Do you want me to write it down? We can check it later. Are you confident?
Not that confident.
Not write it down confident. Okay, all right. Well, we'll hold off then. Any other guesses or answers? 2 7s? Are we write it down confident? Okay, all right. Confidence, I like it. Okay. 2 7s. Any other guesses? Not.
2 over root 14.
2 over root 14. That's close to 2 7s. Interesting. I see another hand. 1? Well, that's a very bold answer. Could be true. It's not impossible.
25 over 27.
25 over 27? Okay. Now I don't know what my answer was.
I feel like I have to go with 0.
Why not? Let's throw it in. We still have a few hundred students here. We can probably...
1/3.
1/3? I like your answer.
So do I.
I like your answer. It feels good to me. It feels like the kind of... We're writing the test right now. And some of the faculty are just like, let's throw in these weird numbers. And I'm just like, no. Let's try to get nice numbers. 1/3, that's a nice number. And 1's a nice number. 2 7s is a nice number. Okay, all right. Any more? All right, well, hopefully it's one of these. Now, okay, so the question, find cosine theta. Now, when we see cosine theta, what do we think? Yeah, we're thinking dot product. Okay, so this is a big clue that there's going to be a dot product involved. All right. So we're thinking to ourselves, okay, there's a dot product, which means we want to take the dot product of vectors. What vector should we be thinking of taking the dot product of? R prime and S prime. Because what are R prime and S prime? They're the directions on the tangents, right? So when we're talking about angles, we really are thinking like, instead of thinking of it in this fashion, we should think of it as if we zoomed in. Now I have to remember what colors I used. If we zoomed in, we'd see it would look very much like two intersecting lines. If we were to zoom in very close, so this is us zoomed in. We should indicate zoomed in. All right. And so we want to say, well, they look like lines, so we should use the direction of the lines. And we get direction of motion, in this case, because we're talking about motion when we talk about these curves, by looking at the derivatives. Okay, so, good stuff. let's take r prime and s prime. What is r prime? Should I just do it quickly, or should we do it together? All right, 2 times t plus 1. I like that, and I answer. Good. Next one? 2e to the 2t. The 4 goes away because it's a constant. Okay, the next one. Cosine t. Derivative of sine is positive cosine. S prime of t is 8e to the 4t. What rule did we use to bring that 4 down? Chain rule. Minus 1 goes away. It's a constant. Derivative of 5 minus tangent 4t. So minus 4 secant squared. Don't forget the 4. The 5 goes away. Derivative of t squared plus t plus 3. 2t plus 1. All right, now we don't want to take the dot product of these because we don't want dot products of functions. Not that we can't take the dot product function. That's perfectly allowed. We're interested in the ones with numbers. So what's our next thing to do? Plug in 0 for t. So we're going to be getting r prime is 0 and s prime is 0. Okay, so r prime is 0 is 2, 1. Cosine of 0 is 1. E to the 0 is also 1. S prime of 0 is 8. Negative 4. Secant of 0 is 1. 1. 2 times 0 is 1. And then the plus 1 is 1. All right. So, from the formula sheet, we know that cosine theta will be coming from taking the dot product. And one other thing, what else do you need to do? Divide by the magnitude. So we've done the hard part. We've found the vectors. Now we just actually have to carry out the computation. So it's 2, 2, 1 dot 8, negative 4, 1 over, and then the square root, because magnitude involves a square root, and you square the entries. 2 squared plus 2 squared plus 1 squared, and the square root 8 squared, negative 4 squared, 1 squared. All right. Upstairs. When we take dot products, multiply entries, and then we add them together. 2 times 8. 16. 2 times negative 4. Negative 8. 1 times 1. It is the 1. Now downstairs, let's see if we can do this. 4 plus 1. 9. Square root of 9. 3. 8 squared. 64. Negative 4 squared. Or is it minus 16? No, it's positive 16. You know. So 64, 16, and 1. Altogether, that makes square root of 81, also known as 9. All right. Well, 16 minus 8 is 8, plus 1 makes 9. Over 3 times 9. Does anything happen nice here? The 9s cancel. And we got 1/3. Okay, 1/3. Ha-ha! Woohoo! Now, I am not saying that if you got anything else other than 1/3, you got it wrong. Probably was a small mistake. Now the question is, did you understand the process? Because when we grade, the goal is to grade process. So think about, okay, did I find my derivatives? Like, I don't know if, maybe this will not shock you. I'm working on writing a problem. It involves a derivative. Okay, so that's like 1/3 of the points. Can you take this derivative? You know, oftentimes people are like, oh, it's either like you get 0 or 10. No, you can get a lot of points along the way. We're looking for process. And so make sure you understand what's going on. So any questions on part A? All right. Well, now that we're almost out of space, part B, find the plane which contains the tangent lines to r of t and s of t at time t equals 0. Now, I'll be honest with you, I actually don't know the answer to this one. I haven't computed it yet. But did anybody compute it? Yes? Do you have an answer? Yes. Can I write it down?
Sure, go for it.
All right.
6 times x minus 1 plus 6 times y minus 5 minus 24 times z minus 3 equals 0.
6 times x minus 1 plus
6 times y minus 5
okay.
minus 24 times z minus 3
Times z minus 3 equals 0. Interesting choices you've made here. Okay. Good. We'll talk about these choices you've made. I actually, this feels good. This feels good. Any others?
X plus y minus 4z equals negative 6.
X plus y minus 4z equals, and you said negative 6? Okay. All right. Any others? All right. So how many different answers do we have so far? 1. These are actually the same plane. So I hope it's a good thing that they both got the same plane, right? Now you're probably like, that does not look like the same plane. We'll talk about it. We'll talk about it. Okay. So we're asked to find a plane. What information do we need to find a plane? Point and a normal vector. Okay, what do we have so far? Do we even have a point? Well, we can find the point. How do we find the point?
By using the angle that we just worked.
Maybe not the angle.
Plugging in t for r of t and s of t.
Okay, so we can plug t equals 0 into r of t or s of t. Which one should we plug in? Yeah, the easier one to compute, right? It doesn't matter. Because they're supposed to be at the same point at the same time. So if there's one that looks easier for you to compute, plug it into there. I'll just go into r. So we have our point. All right, so that's r of 0. And 0 plus 1 squared? 1. 4 plus e to the 0? 5. 3 plus 0? 3. And you'll notice the 153 that was mentioned in one of the solutions. That's where that's coming from, the 153. So now we have a point. Okay, so next up, the vector, the normal vector. How does one make a normal vector? So if you're making a normal vector, should we be using the dot product or the cross product? Cross product. For one thing, the dot product doesn't make vectors, but cross product does make vectors. Now, why do we love cross product for making normal vectors? What's cool about the cross product? Perpendicular. Yeah, the cross product says, you give me two things, I'll make something perpendicular to both of those. The normal vector is the thing that's perpendicular to the plane. So we're like, cool. So all we have to think of is two things in the plane, two directions. Take the cross product, and we're good. Do we have two directions in the plane? Yes, what are they? R prime is 0 and S prime is 0. These direction vectors of the line, because the lines are in the plane, those vectors have to be in the plane. So the normal is going to be found by taking the cross product. So we don't have to rederive the vectors, we're just using them in a different way. So this question is, one nice thing about it is we get to see, we're using dot product and cross product. And we're sort of seeing, oh, here's the situation we should use the dot. Here's where we should use the cross. Okay, so how confident are we in our cross product skills? Which is what I'm really asking is how quickly can I go through and write this down? Or should I go through it slowly? People seem okay. I'll just start. So I do diagonals. So remember, we're going downhill, and if we hit the side, we just wrap around to the other side. So I times 2 times 1 would be a 2i. J times 1 times 8 would be an 8j. K times 2 times minus 4 is a minus 8k. Those are my downs. Now let's do my ups. 8 times 2 times k, that's minus 16k. Now, that's a positive 16k, but because we're going up, we have to subtract it. So remember, you add the downs, subtract the ups. And I do a little bookkeeping just to help me put everything together. So I'm putting the i's on top of the i's, j on j, k on k. Okay, next one, minus 4 times 1 times I. That's a minus 4i, and we subtract. 1 times 2 times j, that's a 2j, but we need to subtract. So we get 2 minus minus 4 is 6. 8 minus 2, 6. Minus 8 minus 16 is minus 24. Now, we pause and be like, oh, these are big numbers. 24, But then we remember, when we're talking about a plane, we talk about a normal vector, not the normal vector. There's a difference between a and the. What's true? Are normal vectors unique? And why not? Okay, so there's two questions in here. Are normal vectors unique? No. Why not? You can scale them. So here's something we can do. What we can do is we can say, I'll pull out any common factor. And this is a good thing to do if you have to do other things like find magnitude or work with normals and say, well, 6 divides all these terms, so 1, 1, negative 4. And now, instead of working with 6, 6, negative 24 as the normal, I can say, hey, I'll just use this 1, 1, negative 4. It's easier numbers, so I like working with that. So the difference between these two is whether or not you scaled. Now, which one gets the points? They both get the points. As long as the question says find the plane, these are both correct answers. Now, if it said find the plane in a very specific form, well, then you have to get it in just that form. But these are both the right answer. Now, we're not quite done. We should finish up the process. Now that we have the normal we want to use, this is the simple normal, we say that gives us our coefficients. So we have coefficients of 1 and 1. So there's sort of a hidden 1 in front of the x and the y, and negative 4. So the 1, 1, negative 4 gives us our coefficients. But then we still have the question, what's in the box? What's in the box? What's in the box? What do we put there? And how do we find it? I mean, what's the point of me asking this question? How do we find it? Oh, we plug in the point, right? So plug in 1 for x, 5 for y, and 3 for z. 1 plus 5 is 6 minus 12 makes negative 6. And so our final answer is x plus y minus 4z equals minus 6. And there we go. Okay, and now in the last 5 minutes of class, no, we have time. All right, any questions? Yes?
Could you also write it in the form like x equals something
Well, so you can rewrite this in lots of ways. The convention for planes, the reason we like to write planes in this way, where you have the x, y, z all on the same side, is so you can easily spot the normals. So we almost always write it as, something x plus something y plus something z equals a number. Are there other ways you can write it? Yes, but I do think there's a bias to writing it in this way.
Do you have to solve for what's in the box? Because the first person, they didn't do that. They just...
Well, you don't have to. You can if you say x minus your x coordinate, y minus y coordinate, z minus z coordinate. That's another way to do it. And it gets the points. It's however you remember it. That's the thing. Do it the way that you'll remember it. All right. Well, we do have more than one slide. So, okay. Goals for today. Well, we'll do a quote, Richard Branson. And he said, "You don't learn to walk by following rules. You learn by doing and falling over." Which is to say, you're going to make mistakes. And that's how you learn. When you see babies, they don't try to walk one time and say, all right, that's it. I'll just sit in for the rest of my life. No, they keep trying. And they succeed. A surprisingly large number of babies learn to walk. It's not an easy thing to do. We take it for granted how easy it is because we've been doing it for so long. But because they persist, they succeed. And when you persist, you'll succeed. So keep going. Keep going. Now our goals for today, very simple. We're going to talk about motion, which means position, velocity, acceleration. We're going to be talking about that for this week. We'll introduce the idea of the osculating plane and talk about differentiation. We're going to talk about integration. And spoiler alert, you do the same thing. Work one entry at a time. Okay, so we'll start with motion. We've already mentioned that we think of r of t as being our position. We've already talked about how the derivative, that's how position changes, which has a name, velocity. All right, so that's not too surprising. We also mentioned that if you take the magnitude of velocity, which is now not a vector, this is a number depending upon t, that's speed. So speed is essentially velocity, but you lose information about the direction that you're going. Or you can think of it the other way around. Velocity is speed, but it also says, I know where you're going. Okay, so sort of the new thing is the second derivative. I mean, the derivative was so nice, we said, let's do it twice. And so if you want to take the second derivative, it just says take the second derivative in every single slot. So what does the second derivative mean? Well, it's how the first derivative is changing. That's what the second derivative is telling you. But we said the first derivative is velocity. So it says, okay, that's how velocity is changing. And then the physicists say, well, let's give that a name. We'll call it acceleration. And everyone's like, cool, more alphabet. So we have now acceleration, a of t, that refers to the second derivative. We've already talked about how you can use information about position and velocity to get tangent line. And so that says that's capturing the movement of the curve at a particular point. But you say, well, could I use more information? So what if I used not just position and velocity, but position and velocity and acceleration? You say, well, what do we have? Position we should think of as a point. Velocity and acceleration we should think of as vectors. So we have 1 point and 2 vectors. So that sort of says, aha, idea. Let's make a plane. So what we'll do is we'll have the plane has the point, and at the same time, it has the vectors that tell you motion, r prime, and acceleration, r double prime. So the normal will come from taking r prime cross r double prime. And in essence, it's saying, you know, this particular plane is very closely matching the behavior of what the curve is trying to do. And we're going to give it a name. We'll call it the osculating plane. So the osculating plane is trying to capture the behavior of the curve at a particular point. Does anybody know what osculating means? Have you seen it before?
Like in a watch, like a mechanical watch has an oscillator that goes back and forth.
Well, you might be thinking of like an oscillating, OSCI. This is OSCU, OSCU. But oscillating, yeah, because it sounds like that word. So it's very tempting. Osculating. It means to kiss, you know. So it's the kissing plane. I don't recommend you go to your significant other and say, hey, let's meet up together and do a little bit of osculating later on. You know, it's not going to go well for you. So, but anyways, the idea is it's the plane that just kisses the plane. All right. Any questions about this part? Okay. How are we doing on time? We're doing okay. So, find the osculating plane at time t equals 0 for the curve. R of t is 4 tangent t plus 2, e to the 3t minus sine of 2t, comma, log of 1 plus 4t minus t plus 5. So we have here a bunch of pieces. Okay, we have to get going if we're going to make it to the end of the class. So how did people do? I feel like this became an unexpectedly like, oh, I have to take derivatives and I got to remember rules and like chain rule, that's like a real thing. So how far did people get? Did you get r prime? Did you get that? I'm not saying you stop there. Okay, all right, good. Did you get to r double prime? Nice. Did you plug in 0 for everything? Okay, all right. Now, you'll have more time during an actual exam. All right. Did you take a cross product? Okay, a couple. Do we have an answer? Like, if you got to a cross product, all right, another.
Negative 43x minus 64y plus 36z.
Maybe. Negative 43x, what was it?
Minus 64y plus 36z equals 30.
Well, maybe. Should we find out? Okay. All right. So, this is a popular question. The reason it's popular is because it tests you on a couple things. You have to test derivative, second derivative. You have to say, okay, I understand plugging things in. You have to say cross product. So, that's a guess. I don't know because I don't think I've actually done this one. So, derivative of tangent, secant squared. The 2 is a constant. Derivative of e to the 3t, 3e to the 3t. Derivative of minus sine 2t, minus 2 cosine of 2t. Derivative of log. I put whatever's inside the log downstairs, and the derivative of that goes upstairs. So 4 over 1 plus 4t, and a minus 1. All right. That's first derivative. Now, second derivative. How does one take the derivative of secant squared? What's the rule you need? Chain rule, because it's secant inside the square. So what will happen is the 2 will come down. So this is 4 times 2 times secant times the derivative of secant, which is secant tangent. Derivative of 3e to the 3t, another 3 comes down. Derivative of minus 2 cosine 2t will become a plus goes rid of cosine is negative sine. An extra 2 comes out, so 4 sine of 2t. The derivative of 4 over 1 plus 4t is negative 16 over 1 plus 4t squared. Now, if that sounds weird, here's the idea. This is really 4 times 1 plus 4t to the minus 1 power. And chain rule. All right, so the minus 1 comes down. That's where the negative. The 4 sticks around. Then the derivative of the inside will give another 4. That's why you get up to 16. And it's going to be to the negative 2 power. That's why you get squared downstairs. And the derivative of minus 1 is 0. So there's the function, first derivative, second derivative. Okay, so we need to get r of 0. We need to get r prime of 0. And we need to get r double prime of 0. So the osculating plane needs all of that. So we plug it in. R of 0, we get 0, 2, 1 minus 0. Log of 1 is 0, minus 0 plus 5. So 2, 1, 5. R prime of 0. We get secant of 0 is 1, so that's a 4. 3 minus 2, that's a 1. Then here we get a 4 minus 1, that's a 3. 4, 1, 3. R double prime of 0. We get a bunch of stuff, but tangent of 0 is 0, so that makes the whole first entry 0. 9 plus 0 is 9. And minus 16 over 1 is minus 16. Okay, so that's that. All right. Now, the next step in our trip to finding the oscillating plane is we take the cross product. R prime is 0 crossed R double prime is 0. I, J, K, 4, 1, 3, 0, 9, negative 16. And it's times like this I say to myself, I really should have checked these numbers earlier. But we just go ahead. It is what it is. And we start filling in values. So we get minus 16i plus 0j plus 36k. Subtract 0k. Subtract 27i. And then we're going to add 64j. Which makes this a negative 43, a positive 64, and a positive 36. Oh, where have we seen numbers like this before? Oh, ho, ho, hey, hey. Although, did I copy something down wrong?
No, I messed it up.
Oh, you're only going to get 9 out of 10. Art history major, here you come. No. Great job. Don't do that. Be smart, don't start. Okay, so we have the normal. We're in the home stretch. Minus 43x plus 64y plus 36z equals something. And this is the time when I say, oh, maybe you should have put in like minus 43 times x minus 2. Well, but all right, let's just put it in. Okay, so minus 43 times 2, 64 times 1, 36 times 5. That's minus 86 plus 64 plus 180, which is a number. And of course it is. And, well, what can we say? If you take 180, subtract 86, that would be 94. If you add 64 to 94, that gets you 158. And so that's our answer. Minus 43x plus 64y plus 36z equals 158. Just like you thought. Don't worry. We normally do a better job of screening these questions. But the process, right? The process, we understand.
Can we leave it as equaling 0 if we put the points into the...
Yeah, if we feel like x minus 2, y minus 1, z minus 5. Or you could just say, and it's these three numbers added together. Because the instructions say, don't have to worry about simplifying. Now, we're going to do a couple of things, but really quick to finish up. We'll save this for next time. We can take derivatives by going term by term. So we're going to do antiderivatives the same way. Go term by term. Each term gets its own constant. There's the same idea for definite integrals. So, suppose you're asked this question. Find the definite integral from 0 to 1 of this vector valued function. Vector valued because it's integral of a vector. What do? It says, hey, just integrate each piece. So we're going to integrate the first slot. We'll integrate the second slot. And then we will integrate the third slot. Okay. Does anyone recognize this antiderivative, or how to integrate this? It's e to the t plus t, and now you evaluate 0 to 1. Does anyone know the antiderivative of 4 over square root of t squared plus 1? 4 arctangent. T evaluated from 0 to 1. And then there's this one. Okay. That's not on our formula sheet. When we plug this in and evaluate, we get e plus 1. That's when you plug in 1. E plus 1. Subtract. What do you get when you plug in 0? You get 1. E to the 0 is 1. When we plug in 1 into arctangent, what do we get? Arctangent of 1? You can figure it out from the formula sheet if that helps. It's pi over 4. Arctangent of 0? 0. And then there's this thing, which gives us e in the first slot. It gives us pi in the second slot. But what is that thing? I've been avoiding it, but I shouldn't. I should respect it. Do you recognize it? It's a trick we kept pulling on you over and over in Calc 1. Do you recognize the square root of 1 minus t squared? It's part of a circle. It's 1/4 of a circle. So this is our way of saying, hey, not everything has to be done by antiderivatives. You can use other tools. So it's 1/4 of a circle that has radius pi. Sorry, it has area pi, so 1/4 pi. So that's the answer. Now, one last thing. Like I said, we'll come back and do this one next time. So we can integrate. We're going to talk about integration next time. But suppose we have a curve. So here's the curve r of t. And I have this curve, and I've marked 2 times. And I have some questions. How do we interpret the following? The integral from a to b of r prime of t dt. What is that? It feels like r of t, but then we evaluate. So it's a vector. It's this vector right here. This is your r of b minus r of a. If we were channeling our physics teacher, they would call this displacement. How far you moved. What's the difference between the first and the second? It's the distance from start to finish. Now that's if you integrate and then take the magnitude. But what if you take the magnitude and then integrate? That is next time. So that's what you have to look forward to. That's it for today. Have a great day.